So let's get started. First off, I'd like to thank everyone for joining us this year at MLOps Worlds 2021. I hope you found this just as insightful and exciting as I have. Before I introduce our next speaker, I'd like to just go through a quick reminder to check out our partners at the booths. I think the prizes are still going on, so you have a chance of winning a $100 Amazon gift card. Now, without further ado, I'd like to introduce our next speakers, Jitendra Pandey and Jagane Sundar. Jitendra is the co-founder and CTO of Infinstor Inc, which is a multi-cloud ML platform that offers integrated compute, storage snapshots, and MLFlow services for machine learning training and serving at scale. Jitendra has more than 10 years of experience with open source big data systems and Apache Software Foundation. He is a committee and PMC member for Apache Hadoop Ozone project. Jitendra holds a master's degree in computer science from Stanford University. Jagane is a seasoned entrepreneur and software executive. He is the inventor of InfinSnap and InfinSlice for cloud object store. His expertise include machine learning infrastructure, cloud distributed computing, Hadoop, container, Paxos, RAFT, XAB, and old school Linux software engineering. Jagane is a seasoned entrepreneur, having found multiple technology startups, raised capital, and led them to successful exits. They will be giving us a talk on unlocking the power of MLFlow with a multi-cloud compute infrastructure. Please give a warm welcome to Jitendra and Jagane.
Thanks, Peter. Hello, everyone. As Peter introduced me, I have been involved with big data open source for almost 12 years now. I'm a member of Apache Software Foundation and a committed PMC member in Hadoop. I have spent a lot of time developing HDFS and also Hive query execution in my work at Hortonworks. Currently, I'm co-founder and CTO at Infinstor. I'll say a few words about Infinstor. Infinstor is a multi-cloud ML platform. We bring in data lifecycle management and compute infrastructure and MLOps onto a same platform. As part of data lifecycle management, we have patent pending technologies, InfinSnap and InfinSlice. InfinSnap is a snapshot of cloud storage. For structured data, we have solutions like Delta Lake, which provide time travel functionality. But for unstructured data, we need snapshots of your data in the cloud buckets, and Infinstor platform provides that, which is very important for tracking your experiments and tracking your data that is used across your experiments. InfinSlice is an improvement on InfinSnap, where you can query for data ingested between two given timestamps. And this is very useful for use cases like continuous training, where you have data coming in on a daily or weekly basis, and you want to train on the newer data that is arriving in the time frame. In the rest of the presentation, I'll primarily focus on compute infrastructure and how it works closely with MLFlow to bring in some unique capabilities that are very effective for data scientists to produce better models in the fastest time and at the lowest cost. So at a high level, the key challenge that these ML platforms are trying to solve is to produce better and more effective models. Typically, at an enterprise, a project starts with some good promise. There is an initial model which is doing very well, and now we have to take it to production. In the productionization process, it has to go through these iterations and improvements, and where we have to cover all the use cases. We have to scale to the data requirements, and we want to try different algorithms to get to the right level of accuracy that our business case demands. And in this process, there are hundreds of iterations, and it costs hundreds of dollars per iteration. It takes hours or days per iteration. So we are talking about significant amount of data scientist time. And these iterations continue even after you go into production, because new data arrives or there is a data drift. So you have to continuously iterate. And across these iterations, data scientists want to experiment with new algorithms, which might require new hardware, the different hardware available in different clouds. For example, if you want to try some hard TensorFlow algorithm that benefits from TPUs, you want to go into Google Cloud. And across all these experiments and runs, we have to track the history of data and as well as the experiments. Here we are talking about the intermediate data as well. And data scientists, when they are running an algorithm, they are debugging, they want to scale up and scale down because you want to debug on some smaller subset of data, then you want to scale it up and run it on the full size of the data. So all this ability is required from the platform. So Infinstor platform tries to solve exactly this problem. As I mentioned, we bring in the compute and storage along with MLFlow, and these systems work together to address this. We have snapshots for data, as I mentioned before. MLFlow provides the experiment tracking, but we also track all the intermediate data that is produced at each stage of processing, because a typical ML pipeline could be pretty complex. You are doing some feature extraction work, you are doing some pre-processing, data cleansing, and then you implement some ML algorithm based on PyTorch or TensorFlow. And all these different stages produce an output which is useful for data scientists to look at, to investigate into the behavior of their model. So Infinstor keeps track of all this intermediate data and along in its snapshots. And the platform provides you ability to reuse the intermediate data. I will give some certain examples of this use case because that can save significant amount of time and cost. Now, if you are processing at a very large scale, you want to partition your data and do parallel processing, because that can save in the data scientist's time and give you a very fast turnaround per iteration. This kind of capability is available in systems like Hadoop for SQL processing, for structured data processing, but for unstructured data, we need this ability along with the flexibility to use any hardware anywhere. So like we know that Hadoop clusters are typically homogeneous. They are within a data center. But for ML, for different stages of processing, we want different hardware. We want to go across the cloud. So, so we want to process at scale, but in a distributed fashion with the flexibility to choose the right hardware for every stage of processing. Effectively, we are trying to provide a trade-off for cost and turnaround time. If the team has budget, they want to procure more machines in the cloud, then the platform gives you flexibility to take advantage of those additional hardware. So, Infinstor Compute Engine is the engine that we have built at Infinstor here, that works closely with MLFlow to bring these capabilities for the data scientists. We integrate with Jupyter Notebook. I will show a screenshot for UI that actually we sit as an extension to the Jupyter Notebook, and from that interface itself, you can define a directed acyclic graph of notebooks. So the platform encourages modular development. If you are doing some pre-processing or feature extraction, implement it in one notebook. And if you have some ML algorithms or doing post-processing or different kind of processing on different data points, that can be done in different notebooks. And the platform lets you define your ML pipeline with all these notebooks as the nodes of a DAG. And then platform also captures the environment that you require for to execute these notebooks in the cloud. It could be a Conda environment, it could be a Docker environment, and once that environment is captured, it gives us complete flexibility to schedule in any environment or any hardware across the clouds that you need. And these if there are multiple stages of processing, then one stage of processing can be in one cloud, or another stage in a GPU in a different cloud, and all that flexibility is available. Partitioning scheme can be specified by the user, but we have some inbuilt partitioners as well that can partition your data for parallel processing. System also provides the ability to schedule executions on a periodic basis. This is very useful for continuous training use cases, or just for inferencing, like you have a data pipeline, you have built your model, but you want to now provide scoring or inferencing on a periodic basis. Then with data is incoming at a particular cadence, then you can schedule the processes at the right cadence. The integration with MLflow is completely seamless. Both the services are available out of the box, and no additional configuration is needed. In fact, we define your experiment, and each and every run ID is granularly assigned to each and every node of execution. So if you define a DAG on our system, the DAG is assigned an experiment ID. Each invocation of the DAG is assigned a parent run ID, and which wraps the execution of all the individual nodes in the DAG. And each node of execution is provided a separate run ID. So you have complete granularity to track your experiments and to track the parameters of your experiment, and also the data that individual node is processing. Similarly, if you have scheduled a periodic execution, each schedule is provided an experiment ID, and each invocation of the schedule has a parent run ID, and each stage of processing gets individual run ID. So let's take an example. This is an example we developed with one of our customers, where they used medical imaging, a bunch of medical images from some of the patients to detect COVID. So the pipeline consisted of 3 stages. In first stage, there is an anonymization, which is more an IO intensive job, where basically just removing some personalized information from the images. In stage 2, we convert from DICOM to NIFTY format, and in stage 3, we apply an inferencing algorithm. We used an open source algorithm to score and to predict whether the patient has COVID or not. Now, in each stage, as indicated in the diagram, that for tracking we are using our multi-cloud MLflow service, but we also track the intermediate data in the MLflow. So actual data is stored in cloud storage, but the index is kept with MLflow. Now, this gives us a very interesting ability that if you, in the subsequent iteration, you can specify MLflow run ID as an input. So this is a feature of our platform that when you're specifying the input, you can say that just this specific run ID is in my input. And now the system will only execute stage 2 and 3, and the output of the first stage will be reused. Now, this capability can be generalized because if you develop a feature in stage 1, and store the index in MLflow, then that run ID can be used as a feature across experiments. So using this, we can save significant amount of training time and also cost. So how does it look in the runtime? Because we saw that this is a 3-node graph, but at runtime, we are partitioning the data. So at partitioning, when we partition it, it splits into a lot of nodes, and now these are running in parallel into many parallel VMs. Although I mean this node, this kind of execution graph gives us a faster turnaround time, because like in this case, we were able to reduce the runtime from 12 hours to less than 2 hours by using the nodes across cloud, but when you are doing so much of parallel processing, we know that in distributed processing, the probability of failure also increases. So what happens if this node fails? Then again, we can use MLflow tracking to handle this failure, because we are tracking each and every node of execution as a separate run ID. And that run ID can be reused when we want to rerun this process. So ICE can restart from the failed stage by reusing the outputs of all the partitions that were executed in the prior stages. And this fast recovery is possible because we are tracking the run IDs at the granularity of the partition in this example. So what will really happen is that you will just rerun the failed node, and an MLflow service will give you the index of the outputs or the data which is already successfully run, and produce the final results. So this is our screenshot of the UI. As you can see that we closely integrate with the Jupyter Lab notebook. We have an extension on the left hand, and from here you can access your data, you can define your tag, you can capture the environment of your processes. We call all these notebooks as transforms because they are essentially transformation on the data. And in the front here, this is a screenshot of a DAG in execution. So it is the same DAG, but I'm running a much smaller subset of data here, where first 3 stages are the anonymization, 3 different partitions of the anonymization. And we can see that because of the splitting, we are achieving now pipelining, because the first node of the in fact the first partition of the 3rd stage has already started, while 2nd stage is not complete. The green shows that the nodes which are already completed, while blue shows the nodes which are in process. And this kind of pipelining actually gives a much faster performance when we are executing them at the scale. This is our MLflow service screenshot. The experiment ID defined here is 3, which is assigned to this DAG, and the parent run has a start time, and the name is, these things are flexible. One can choose the names they want, and all the individual nodes of execution are tracked as separate run IDs. You can further click on this, and it will give you all the details of that particular run, including the location of the intermediate data. And the same run ID can be reused or can be provided as an input to any other experiment or graph that you want to execute. So what does ICE really look like inside? So it is a completely stateless, it's completely serverless architecture. We have the state stored in DynamoDB, but there's no long-running server here. That's one of the very important features when you are running at a cloud scale. And all the functionality is implemented in Lambdas. We have a scheduler, of course, which keeps track of the events and when the things need to be run. And the DAG controller is the central piece which tracks the status of each DAG execution and all the individual runs, and which uses a cloud VM manager that abstracts out all the VM APIs. So Cloud VM Manager can schedule into Azure or into AWS or into GCP. MLflow service here plays a central role. As I showed before, that it's not only used for tracking your experiments, but it's also used for tracking your intermediate data, for failure recovery. And DAG controller uses this MLflow service to check the status of the runs themselves. So MLflow service and DAG controller, they work in tandem to make this architecture possible and to scale. Our MLflow service is also highly scalable. It stores the data in DynamoDB, and the APIs are all implemented in Lambdas. We do not maintain any state except for the DynamoDB. The static HTML and JavaScript for the UI is stored in S3 bucket, which has API gateway in the front end, and then there is an Nginx proxy that routes the calls to the right endpoint. We are also working on we have actually a beta prototype ready where we don't really need this Nginx proxy as well. So the high availability of the system is very easy to implement, and because we have DynamoDB, we have backup and recovery. All those things are available out of the box. We have tested this at a very large scale. We have tested up to thousands of concurrent users and tens of thousands of concurrent requests hammering the system, and the system works very well. Yeah, so I will take questions here. My name is Jitendra, as I mentioned, jitendra@infinstore.com. Feel free to send me email, or you have further questions about our ICE architecture, because one thing I forgot to mention that there are certain details about ICE architecture, like we have this DAC controller which is running which could be running concurrently, and then when they are accessing the shared state in DynamoDB, we have to use of some distributed locking. So some of those things, if you are interested in knowing anything more about it, just send me an email, follow us on Twitter or LinkedIn. Thank you.
Yeah, thank you, Jitendra, for the insightful talk. We have time for questions, so if you guys have any questions, just write them on the chat bar on the right-hand side. Yeah, so we'll just give it a few minutes for questions. So in terms of, I guess, from like a question on my end, in terms of integration into into what sort of, do you guys have any case studies on this use with that you guys can disclose about working with different companies? Don't have to say the name, but how they integrated this and what sort of performance gains that they've experienced?
Yeah, so as I mentioned, that this particular example for COVID detection, we did without our platform, what they were running, we used to take easily take 12 hours or more. And when we were able to do this distributed execution, it came well within 2 hours, and with very minimal tuning and very simple partitioning scheme. So and also the ability to use different hardware at different stages of processing provides a significant amount of boost, and also can help cost optimize the ML pipeline.
I see. And I guess when they were transitioning from their previous implementation, were they all just in notebooks and they were just able to port it over?
Yes. So since we integrate with Jupyter Notebook, and you can and our basically UI provides capabilities to capture your environment as well. For example, if you're running it in your laptop or in any SageMaker or anywhere, we can basically capture the environment and let you define the Docker environment or the Conda environment. And once that is stored is tracked in our platform, then it gives us ability to port it anywhere. So in fact, then user does not have to worry about porting it into different environment.
And I really like the idea that it would be able to record the environment of that session. So then later on, it could be it can handle various different environments at the same time. So there isn't any question coming in right now. Oh, yep.
So Jitendra, do you want to talk a little bit about this new world we are seeing, where the amount of data and transferring data out of one cloud to another is insignificant compared to the cost and capabilities of TPUs in a different cloud?
Yes. So what we are seeing is that the amount of processing or amount of time it takes to execute an algorithm, or amount of compute power you need for an ML process, is not only a factor of data, it's also a factor of algorithms. In the sense, if you have even a small set of data, even a small number of, say, images, but if you have too many layers in your neural network, it takes a large amount of processing. Therefore, it is sometimes even more cost effective that we can take this data from one cloud to another cloud and pay the cost of data transfer, and use a cheaper hardware which is available elsewhere. So this is a new trend which we see, because the algorithms are getting more and more sophisticated and complicated, and therefore such a platform can help significantly. For example, let's take another example. These TPUs are available only in GCP, and you have implemented an algorithm using TensorFlow that can benefit from TPUs. But if your whole setup is in Amazon, AWS. So you can continue to do all your pre-processing, data cleansing, and everything in AWS, but just that amount of processing where you are using TPUs, you can schedule it into TPUs in GCP. So that kind of capability is very important in the new world of ML.
Mm-hmm. Definitely, and I guess you guys already have that kind of cost-effective calculation in the back end ready to almost be automated, right? So the moment they need something that that would optimize for speed, you guys have already got that covered.
Mm-hmm.
That sounds amazing. So again, your email is in the title and also your website. So if you guys have any questions later on, please message Jitendra or Jagane. This was an amazing talk, and I really want to thank you guys for joining us today, and want to thank the audience for joining us today.
Thank you, Peter. You've been a great host.
Thank you.
Thank you so much. It was amazing.
Have a great day or afternoon or evening. Yeah. Take care.
Okay. Bye-bye.
Bye.